Hey everyone. So today we're going to talk about the Bohr model, light, energy, and what are called ground and excited states. So to start off, a little bit of background information. So when Bohr designs his model, that's the one with the rings on it. He is designing it mainly because of a problem that Bohr has discovered, should I say, a problem that has been kind of presented. And that is that when materials are heated, they give off only specific colors of light as opposed to every color of light. And this is impossible according to the nuclear model. So Bohr presents his model and he explains how his model, solves this problem. And Bohr breaks down the process into a three-step process. Okay. So Bohr says what's happening when materials are heated up is first that material is absorbing energy. Okay. So right here in the middle of your screen, like in this area right here, this is my like example of a Bohr model. Now it's got straight lines, but I'm just using that to show the different rings, the different energy levels. Okay. So Bohr says that first, the substance that you're dealing with absorbs energy from some kind of outside source. Okay. And that could be from like heat or electricity, light, or, whatever. Okay. And Bohr calls this the energy absorption phase. Let me write that in black so that you can see that better. Okay. And you know what? Like, to make this simple, let's focus on the element that Bohr was focusing on, which was hydrogen. So over here on the right, I've got an orbital diagram. So let me put the orbital diagram for hydrogen. Because hydrogen only has one electron, it just gets one arrow in the 1s sublevel. Okay. So hydrogen is just kind of going along. And then, according to Bohr, it begins to absorb energy through this energy absorption step. Now, it's not really the whole atom that's absorbing energy, it's just the electrons specifically that are absorbing energy. So, the electrons absorb the energy from the flame. Okay, we're just going to use flame as an example for this story. Okay. So when that energy is absorbed, the electrons are able to change their position. They're able to jump up to a higher energy level. Now, according to Bohr, all electrons want to exist in the lowest energy level that they can because that's their most stable state. But this can be temporarily violated if the atom has absorbed extra energy from some kind of outside source. So Bohr says that as a result of this, the electron can jump up to a higher energy level. Okay. Now, in my model, you'll see that there are many different energy levels. How high the electron can jump up is determined by how much energy is absorbed. So that means if you have a source of energy that is much stronger, like say an arc welder or like gamma radiation or something like that, then that can cause potentially a higher jump. Okay. The bigger the jump, the more energy is required to make that jump. Okay. So energy is absorbed and then that electron jumps up. Okay. Now, What this means in our orbital diagram is that this electron right here can actually move up to a higher energy level. So like that one electron that was right here in the 1s, maybe it jumps up into 2s. Okay. Now, this orbital diagram is now violating the rules that we had previously established, and that's okay because it has absorbed extra energy for this to happen. Okay. Now, in my Bohr model, if I just jumped up to the 2s orbital, that would mean it jumps from level 1 to level 2. But this could also, if it absorbs more energy, it could theoretically jump up to, let's say, 3s. And if that happened, then we'd be talking about this jump right here. Okay? Because it would be on the 3rd floor. Now, Bohr calls this second stage the excited state. Okay? So Bohr says that in this excited state, the electron is allowed to violate the rules that were previously established. But there's a catch, because this is not a stable state of matter. It doesn't want to stay this way. Okay? It has absorbed energy, so it's violating the rules, but it doesn't want to stay this way. So what Bohr says is, as that electron kind of tries to relax, it's going to fall back down to its original energy level. And so our orbital diagram, the arrow will go down, it'll fall back down from the 3s to the 1s energy level. And when this happens, okay, that energy that it absorbed, the electron is going to release that energy. Okay? And it's going to release that as what's called a photon. Now you may be asking yourself, what is a photon? A photon is basically a particle of light. It is a particle of light energy. You can kind of think of it as like a package of light energy. Okay? So the energy that was absorbed, it gets released as it goes back down to the ground level. Okay? And Bohr calls this step photon emission. Okay, so Bohr says, actually, let me label this a little bit differently for you guys. Because Bohr says that this like resting state, the normal state for an atom or for an atom's electrons, this is called the ground state. Let's move that out of the way and deal with it later. So, energy is absorbed from some outside force. This causes the electrons to jump to a higher energy level, what we call the excited state. But over time, that electron is going to fall back down to its normal state, which we call the ground state. And when that happens, a photon or a packet of light energy is released. Now, how much energy is released? The amount of energy released has to be equal to the amount of energy absorbed. Whatever energy goes in, that's the exact same amount of energy that comes out. It's kind of like an elevator, okay? If you imagine the electrons as a person, when they go to like a big hotel with a bunch of floors on it, right? They can take the elevator from the first floor up to a higher energy level. And the higher the floor that they take it to, the more energy it's going to take to get there. Okay? Now, there is one critical thing about this analogy. Or actually, I'll get to that in a second, okay? So they can take the elevator up to any particular floor that they want. But at some point, they're gonna have to take the elevator back down to the first floor, okay? So whatever floor they go up to, they have to come back down to the same floor, okay? Whatever energy is absorbed in the beginning, it is lost at the end. However, Bohr also states that this release of energy doesn't have to happen in one step. It can instead, for instance, it can instead happen as two steps. So, for instance, if you go up to the third floor, right, you could go straight down to the first floor, or you could go from the third floor to the second floor, and then the second floor to the first floor. Now, if that happened, okay, the same amount of energy is going to be released. It's just going to be released in two pieces. This first jump is going to release a photon, and the second jump is also going to release a photon. But it doesn't matter whether it's done in one step or in multiple steps. The total energy that is lost will be the same. So what that means is, in my example here, these two arrows, if you were to add the energy lost from these two arrows together, it would be the same as if it had just dropped this, like both floors at the same time. Okay, so whatever energy goes in, the same amount of energy has to go out. Okay. Now, this really does explain what the problem was. And that's because instead of all the possible amounts of energy being released, right? Instead of it being kind of a spectrum, instead what we're dealing with here is a very specific amount of energy, because the amount of energy that it takes to jump up to a particular floor, that amount of energy is an exact number, okay? So as a result, the energy that's lost is also an exact number. And this does solve the problem that had been plaguing people. And here's why. Because energy is inversely proportional to wavelength. Now, what do I mean by wavelength? In order to talk about that, we have to talk about what light is, okay? Light behaves most times as a type of what's called electromagnetic radiation. And what that means is it moves through space as a wave. We can see an example of that right here, kind of near the top, okay? So it kind of goes in this up and down pattern, okay? But how quickly it goes up and down and how much distance it'll cover in the time it takes to go up and down are affected by how much energy it's got. So let me explain, okay? Let's say I've got my wave of energy right here, okay? If this wave is like the standard amount, okay? If it had more energy, what we would see is it would start going down, up and down faster, okay? Oppositely, if it had less energy, we would see that it would go up and down slower, okay? So this top one has less energy. This one has excuse that. This one has more energy. So a wavelength is the distance from the top of one peak to the top of the very next peak. Okay? It's basically a measurement of how fast it will go up and down. Okay? So if this middle one is our normal peak, or our like kind of middle energy, the one with more energy, what we can see is the wavelength, the distance from peak to peak, is actually quite a bit shorter. And conversely, our lower energy wave, the wavelength is quite a bit longer. Okay? So the more energy you got, the shorter the wavelength. The less energy you've got, the longer the wavelength. Okay? So why does this matter? Okay? Actually, I'll leave that for now. This matters if we look at the visible spectrum or the electromagnetic spectrum. Okay, this is a chart of what's called the electromagnetic spectrum. And this is all the different types of electromagnetic energy that there are. And we can sort these by wavelength. Okay? And what we see is shorter wavelengths have more energy, and those are things like gamma rays and X-rays and UV light, ultraviolet light. But when we get to right here, right about in the middle, we have what's called visible light. And visible light is all the different colors of light that we can see with our eyes. Okay? All of the different colors that we can see fit in this tiny little sliver right here in the middle of the spectrum. So what this means is anything with a shorter wavelength than something that falls in this tiny little piece, our eyes can't see it. So we can't see gamma rays, we can't see X-rays, we can't see ultraviolet rays. Okay? We can see what's in the visible spectrum. But if it's got a longer wavelength than this, like infrared light or radio waves, microwaves, things like that, this becomes undetectable to our eyes again. So we can't see this, we can't see this, we can't see this, we can't see this, and then all of a sudden, poop, this little piece, we can see it, and then beyond that, we're back to can't see it, can't see it, can't see it, can't see it. So the only things that we can see are in this tiny little piece right here, okay? So here's the thing. Each of these colors corresponds to a specific wavelength of light. And because, as I just established, because the wavelength is connected to the energy, right? They're opposites, they're inversely proportional. Because they're connected, what this means is any particular color of light has a specific amount of energy that is tied to it. So when we see a particular color of light from these heated materials, what that means is that is an indication of how much energy is being released in that particular photon. Okay? So, for instance, let's take my example right here, and let's, for the simplicity's sake, right? Let's do the one step first. Okay? So, in my example, energy is absorbed, the electron jumps up to the third level, and then it falls back down to the first level. And when that happens, a photon or a packet of light is released. Now, that photon is holding a specific amount of energy, the amount of energy it takes to go from the first floor to the third floor. So, because of that, that amount of energy is related to a specific wavelength of light. And because that specific wavelength of light, if that specific wavelength of light is in the visible spectrum, it will match one of these colors. And let's just say that that color for this one, because it's a 2-level jump, let's say that this is blue. Okay? So Energy is absorbed, electrons jump up, and then when they release their photon, the amount of energy that is released in that photon corresponds to a particular color of light. And in my example, I'm saying, hypothetically, this is blue. But let's consider the other option, the other example, right? Let's say I'm not doing the one step right here. Let's say I'm doing the two-step drop, like this and like this, okay? Because these are two different jumps, there's going to be two different photons released. Let's just go like that. Okay. Now, the bigger the jump, the more energy released. But I told you previously that these two jumps added together would be the same as this one big jump. Okay. So what that means is this jump and this jump are going to have less energy than that previous photon that I showed you where I called it blue. Okay. Now, if we look at the gap between 3 and 2, it's slightly smaller than the gap between 2 and 1. What that means is the photon released from this jump from 3 to 2 is going to have less energy than the jump from 2 to 1. And both of these together are going to have less energy than the jump from 3 to 1. So if I look at my spectrum right here, blue is like right here, okay? So I've got two smaller photons, right? So let's say it's like red and yellow, okay? Now, which one's red and which one's yellow? Because red has a longer wavelength, that means it has less energy. So the smaller the jump, the less energy. So we'll say that this one is red. This one is the bigger of the two jumps, but still smaller than the 3 to 1 jump. Let's say that that is yellow. Okay? But remember, if you were to add the energy from these two photons together, it would be equal to the energy of that one photon from 3 to 1. Okay? Now, this doesn't mean that we can see every single transition that there is. Okay? Because remember, it's got to be in the visible light spectrum for us to be able to see it. So let's consider a different or a similar example, but, slightly different. Let's say instead it was jumping up to this third floor. Okay? That means that it's got to go back down, or I'm sorry, I said third. Let's say it was jumping up to the fourth energy level. And let's say there was two different ways for it to go back. Let's say it could either go back in one big jump or in several individual jumps. Okay? There's something I want to point out to you guys. Remember, in order for our eyes to be able to see it, it has to be in this very narrow band of the visible light spectrum. If it's too big, like if it has too much energy, it's going to be like UV light or X-rays, and we're not going to be able to see it. Or if it doesn't have enough energy, it's going to be like infrared light or radio waves, and we're not going to be able to see it. So in this situation, it's possible that both of these sets of jumps could be occurring, right? Like let's say there was multiple electrons that this is happening to. What this means is our smallest jump, for instance, could be like infrared light. And then the second smallest jump could be like yellow. Our second biggest jump, because it has more energy than the first two, could be like green. And this huge jump, the one from 4 to 1, could be like ultraviolet light. Okay? There's 4 different jumps here, which means there's 4 different particles. There's 4 different photons. But here's the problem. Our eyes cannot see infrared light and our eyes cannot see ultraviolet light. So what that means is, in this situation, we would only see yellow light and green light coming off of the material. So I think this about does it for this presentation. If you have any questions, feel free to stop by anytime.